Hello YouTube, today I'm going to talk about power series and introduction to Bessel function. So at first we will talk about power series. So by the theory of Taylor, we can assume that some continuous function can be expressed as a sum of a coefficient times a x to a certain power over all the possible integer powers. So a sum of ai, so a certain sequence, times x to the power y. Um, so we will consider the first differential equation, y differentiated twice plus y is equal to 0. So we differentiate this expression once. So you can swap the differential and the sum. So you get the the derivative of this. So when you derivative ai, it doesn't depend on ai. And when you derivate x to the power y, the y goes in front, so the y here, and the power of x is decreased by 1. So here you can notice that if y is equal to 0, we would have a negative power here, and this is not something we like in continuity, because we prefer to have a positive exponent. That would generally, if you are dealing with a differential equation that has negative power, it's not fine. But here we can notice that, yeah, when y is equal to 0, y multiply the whole thing. So actually we could start this sum at 1, but it doesn't really matter. Here we do the same reasoning. This isn't dependent on x, and um, when we differentiate it, the I minus 1 goes in front, and we diminish the exponent by 1. And we can either start it at 2 or at 0, because this cancel out in 0 and this cancel out in 1. So we do a change of variable because we have terms that are equal to 0. So we do a new variable I that is equal to the previous variable minus 2. And we get this result. So now we will sum them and factorize by x to the power y. This technique is very frequent. It's very used. So we get this thingy. So we can express it as a vector of the polynomial space. So if this is equal to 0 for all values of x, this means that for all I, this is equal to 0, because we have this equation, and 0 in the polynomial space is 0 on all the components. So all of this is equal to 0. So we rewrite that, we do a little bit of subtraction and division. This is never equal to 0, so we can divide. We get this result. Now we will separate odd and even term, because you can see that the sequence goes every two steps. So we can notice that for even terms, here we have an even power, in an even number to the power factorial that divides minus y to the power I times x to the power that even number, sorry. And we took a0 to be equal to lambda and mu to be equal to a1, and we do the same thing here. So this result is gotten by doing the recursion on an odd and even sequence, and on splitting the part when it's odd and when it's even. So once we get this, we can notice by the theory of Taylor that this is equal to cosine x and this is equal to sine x. So we get lambda cos x plus mu sine x. But when we notice here the equation, this is strictly equivalent to you derivate twice and you get the opposite of the first function, because y prime is equal to minus y. We can quickly verify it. If we have lambda cos, when you differentiate it once, you get minus sine, or minus lambda sine. And when you differentiate it once again, you get minus lambda cos. So you get minus the first function. Same goes for mu sin. Then now we will talk about the Bessel's differential equation, which is this one. So we have this function that is kind of tricky, and we don't know exactly how to express it. So we don't have any easy function to solve this, and Bessel proposed to solve it using power series. At first, we can also note that there are two versions. You can also divide in every term by x squared, so you get so the second differentiation of y with no coefficient in front, well, no variable in front, but it's strictly equivalent. And so we have this equation. We will assume that yx has this form. So we replace using the previous result of y prime and y to the differentiated twice. So we have all of this. We factorize. We do a change of variable of this power in order to have x to the power y. And yeah, we get this result here. You can notice that uh, I to the power minus 2 is not properly defined. Well, I assume that we define it for 0 and values over 0, and when it's negative, it's just 0 because it cancels out, and because it's kind of cool for writing. So that's it. Oh, also I did notice we have alpha a certain coefficient. So we have all of this. We simplify. We have all of this that is equal to 0. So once again, we can express it as a vector in the polynomial space, and it means all the components in front of x is equal to 0. So when we factorize by ai, we get this plus a to the power I minus 2, and once again we got a nice relation. ai is equal to I squared minus alpha squared is equal to minus I minus 2. So with any a0, we have so with all a0, if we start at a1, we don't have any a minus 1. So this is always equal to 0 because of the previous relation. Because here we would have 0, so a1 is equal to 0. a2 is equal to a0 over 2 to the second power, so 4 minus alpha to the second power. And with a3 we have something in function of a1 which is equal to 0, so we can notice that the function does not have any even terms. So yeah, for k, a2k plus 1 is equal to 0. And when we simplify, so do the recursion with this, we get this result here. So there are 3 dots here, obviously. So 1 plus alpha times 2 plus alpha times 3 plus alpha dot 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 times k plus alpha. So now remember we have a differential function that depends on alpha. So we call j of alpha the Bessel function of the first kind of order alpha. J alpha that is equal to a0, so a certain function, a certain number, times all of this, and this is a result of doing the recursion. Yeah, and we get this. We choose a0 to be equal 1 over 2 gamma 1 plus alpha. So for integrals, it's equal to 1 over twice the factorial of alpha. So by expanding a little bit and by refactorizing, we get this result here. So you can maybe ask why there is a plus alpha, but maybe you can find it by yourself. It's not really hard. So you get this nice expression that is valid for all alpha, and when alpha is an integer, you can write it like that because you transform the gamma function into a factorial. So yeah, we have this function here. So this function will be easy for so let's take the differential equation. Where is it? Yeah, this one. This function will be useful for spherical, cylindrical Fraunhofer, for example, and various things that require a cylindric geometry, because you will find a Laplacian in a cylindropolar form that would look like this. So this is why it's interesting. So this is what the Bessel function looks like. So you get J0. The only important thing to notice is that in 0 it's equal to 1. And then you can notice that it oscillates. And that's it. So we call the cylindric functions all the function that can be a sum of the complex function, sorry, that can be a function of j to the power nu plus b times j to the power, it's not z here, it's nu. So it's just a sum of j to that order plus b j to the order minus that order. So it's a base of the solutions of this kind of problem, this one here. It's a base, so you can always express it using the initial solutions. So now we can build other functions like the Bessel function of the second kind. So like we have cos p nu over sine p nu times the first kind minus 1 over sine pi nu times j minus nu z. So it can be useful for using another base, so you can use this base. You can also use the modified Bessel function of the first kind. So we call it big Y, and big Y is just I, so the complex variable, so like I squared is equal to -1, I to the power minus nu times the function, apply not in Z but in IZ. So you basically replace Z by IZ, and then in front you multiply by I to the minus nu power. We build the Hankel function to be the sum of first kind plus plus I times the second kind, and we can do with a minus sign also. We have the modified Bessel function K with pretty interesting properties, but I'm not going to detail them, just giving them. We have an interesting result. So when you differentiate um, J0, you get minus J1, so it can be interesting for any integration problem. It also has the following property. So if you differentiate x to the power n jn, you get x to the power n jn minus 1. Now. So we can also express it as an integral. So you can also find this result by replacing by their power series of sine and cosine. So it has this form here, You can also find it using the form we used earlier. So you can notice that you have here cos pi nu, here sin nu, and here you got some nice sin nu, and divided by pi, and it simplifies a bit, but it's kind of tricky, so we'll just admit that. So this result is really boring. Um, is really boring, and well, yeah, and then we can notice that in 0 it's equal to 1 over 2 pi, the integral from 0 to 2 pi of exponential EU sine t. So it's pretty simple here. So an exponential of a complex function that has a sign. And by the symmetry, you can also replace it by cos. For J1, you have the same thing, but you do minus IT. So this is why the nu here is important. And do the same thing with T by symmetry, which is funny too. And then we have another property that come from this property here. When you integrate of x plus x times j0 x dx, it's equal to v, so the top boundary, times j1v. So this result is useful for Fraunhofer diffraction with a circle hole. And at first I thought about doing it, so I just wrote video about Fraunhofer diffraction, but I'm not sure I'm going to do it finally, so I don't know. But this is useful for this. That's all for this video. Thank you for watching. If you have any questions, feel free to ask them in the comments. Bye.